All right, thank you very much. So this talk is partially written by me, but also partially written by another guy at Microsoft, Wolfgang Salvador, hence the attribution here off the top. But today I'm going to be talking about MLPerf, which is a benchmark that attempts to do all kinds of simulation of AI workloads, whether they are training, inference, there's a host of them, checkpointing. But before I go in, I'm getting a crazy echo. Before I get into that, a quick myth-busting portion here. We've been doing a great job. OpenSFS has been doing a great job of trying to cut back all of the FUD around Lustre. And at supercomputing, that was evident. There were cards handed out and lots of placards around Lustre. But that messaging needs to continue. And I think a great way that we might all be able to scale out that impact is by basically publishing MLPerf numbers using our Lustre clusters, whether we're just an administrator that happens to have access to a large Lustre cluster and a good weekend to run a benchmark like that, or we are vendors or integrators. I think the purpose of this talk is basically to educate people about what MLPerf is in order for potentially you to go and publish your own numbers to get Lustre out there. So the outline is system architecture and cost considerations that led to AI being like a really important workload within not just parallel file systems, but any high-performance file systems. What DLIO is, which attempts to simulate AI workloads without GPUs. MLPerf Storage, which built upon that, and why they built upon that. The 2.0 versus 3.0 versions, because they version for every acceptance, like basically round of submissions. I/O patterns that are typical in 2.0 and how you might kind of think about them when designing your storage, how you run it, and some final thoughts. So the system architecture and cost considerations. I think we've probably all seen graphs akin to this. It's a little light on this, so apologies, but essentially it's up and to the right and into the 100 millions for training cost year over year. And while certainly in 2026, inference has taken the center stage in terms of how people are monetizing their models, training is not getting any cheaper, and there are certainly hyperscalers and others out there still doing training, and it is still extremely, extremely expensive. The takeaway from that, especially in training, is that you not only have these long portions where you have to keep all those GPUs fed with data, which are basically the lower steady state bars, but as you make progress through that, much like HPC workloads, there is a checkpointing phase. And much like HPC workloads, they will basically stop feeding the GPUs during that in order for you to get a checkpoint out to storage, typically. And while there's some fanciness you can do to avoid that, you want to do that as fast as possible, because that's essentially an interrupt where you are no longer using your GPUs for what you want to do, which is the training. So minimizing that is hyper important and has been emphasized in terms of what can we do to minimize the checkpointing and make sure that really consistent latency, really consistent bandwidth is given to the GPUs throughout their workload. So DLIO was developed at Argonne National Labs. It was basically an attempt to look at a variety of different AI workloads, LLMs. There's a host. I'll talk about the 3 that they have in version 2.0 later. But it's meant to be a benchmark that you can run without having access to necessarily the latest and greatest GPUs, but be able to reason about how well your storage will perform on those workloads. The principle here is basically on the top, you have a real-world environment. In the case of Azure, it'd be like an ND series node that has a very expensive GPU in it, a large NIC. You're loading storage, you're processing that, not doing I/O during the checkpointing phase, and then you're loading data again. And so there's this little bit of wait while in between the loading stages where the GPU is consuming some amount of time. And what DLIO tries to do is, and this is effectively IO trace replay, if anybody's been familiar with that from the early 2000s or even early 2010s, there's CPU equivalents to this that predated DLIO. But this is really specific to what GPUs tend to do, and especially the frameworks upon which they tend to run. But it executes this by just injecting sleep commands that are well trained upon the GPUs, the architecture that you're doing, and how frequently they sleep, the intervals that they sleep, etc. So MLPerf was basically an attempt to take that great I/O replay layer, essentially, and then create some standardization and rules around like, okay, people want to publish numbers around this. How do you make sure everybody's playing fair? How do you have like opening rounds where people are able to take the code and check it out and see, okay, there's 2 or 3 workloads that we're going to run on. Try it out. If they don't like their results, they can back out before the submissions are fully baked and published. And so they have these rounds, and they're up to round 3, which is still in development. So I'm going to talk more about round 2, which is already completed, and you can go and look at results. But round 3 is still in development. So looking at some of the training workloads they have, there's some image segmentation. So this is like more medical vision kind of processing, image classification, and cosmology. Those are the three main training workloads they have. They have different data loaders, so it's a PyTorch and TensorFlow, but they're moving towards PyTorch and 3.0. And then those actual loaders are used. So like even though they eliminate the GPU from this, they still require you to use those frameworks in order to produce behaviors on the storage that they believe is the most authentic, the closest to actually running this AI workload on your storage without having the GPU. And then there's some information on the actual dataset seeds. I have additional details on a later slide about the breakdown, the I/O breakdowns for these. But there is a very important benchmark that they use. It's called min AU, or average utilization percentage, of the GPUs. And if you fall below that across the entire run, then you fail. And so this isn't too far off of how spec SFS works, where you have to basically hit a specific latency, stay below that latency for your median or mean throughout the run. But basically, this is just making sure that you can keep the GPU fed throughout the training phase. Similarly, there's a checkpointing portion to this for V2. There is not an inference portion of this for V2, but it is coming in V3. And that similarly has different sizes, essentially, of the LLM that you're going to be checkpointing out that are all listed there. Basically, to the right is bigger and more aggressive in terms of the amount of total data that you need to get out in a specific time. This, I'm sure, will be hard to read, but essentially, if you go to MLPerf Storage, the website, you will see a large table of vendors with different file systems, storage system names, etc., that kind of give you an idea of what they did for their results for the V2 round. You can see the organization here, whether it's available or a research system. So if it's fully GA and somebody can go and buy that system, then you're in the available category. There's a storage system name that's just kind of a nicety, and a full PDF that describes the system. There's a bunch of rules around like how much you have to expose to participate here. The storage system type, which they try to classify so that when you're going to look for a storage system, I mean, this is really designed not just for other storage people like us, but also people that are trying to provision storage because they're trying to run some kind of AI model. And so you'll see they classify the storage system type in order to help you go say, okay, I'm running in the cloud, so I need some kind of cloud storage, or I want this on-prem, and so do you want to break it down? And there are very large systems here, there are very small systems here, even individual drives. And so it's not designed to just be like a top 500 kind of thing. It is really designed to allow an end user or a storage architect go and say, okay, within the category of storage that I'm looking for, that I think I need, how many accelerators basically can I power using around what I have available to me? On the right side of that chart, similarly, there is a result across those 3 training workloads. They break it down by both bandwidth and simulated accelerators. And that is, while a little bit redundant, because you can compute one from the other, because it's like, if you're hitting that average utilization, you will have to hit that bandwidth. It's really just the target audience. Some people will just want to know, okay, I have 10 H100s. How much storage? Like, what's a typical thing on here that can basically make sure they're fed while I'm running my training? Checkpointing is much the same. On the left side, the system is fully described. There's a PDF that has all the specs and configurations. And then on the right side, you'll just see a slightly different output in terms of what's actually there. They care a little bit more about usable capacity here. While training data is massive compared to an individual checkpoint, people will frequently keep multiple checkpoints going back. So you can actually have that outpace the total training data set size. So capacity is an important thing for checkpointing, and they pay close attention to it. And then they have both full and subset checkpointing and the number of client nodes that are participating in this. I think I failed to mention on the last slide, there is an integrated client storage as well. So for something like PCC, you would say like, okay, we used 10 or 20 or 100 clients, and they had some, NVMe cards on there if we wanted to use PCC for that. So yeah, again, this is not just another marketing benchmark, although as always happens, it's certainly used by, once you publish, it's used as such by some people. But it's really there to try to get honest numbers within a specific category or class of storage around how many accelerators can be run on that specific storage and configuration. The capacities vary wildly. I mean, again, single drive to over 100 petabytes. On the V2 list, I'm sure V3 will create an even larger range. And throughputs are accordingly diverse. You can't actually sort the list. So you want to go in there and just like hit the bandwidth, and they don't even provide the ability to sort the list from top to bottom. So I think again, just underscoring the intent here, it's really designed for system designers, not for just people looking to create some crazy number. So some I/O patterns, looking at the actual benchmarks themselves. At a really high level, 3D-UNet, the vision training workload is a total bandwidth hog. It's something, anybody that's worked in HPC storage or parallel file systems for a long time, it's a great candidate for Lustre. It runs very well in there. You just have to be able to feed the accelerators. CosmoFlow is latency sensitive. It's definitely not as bandwidth oriented. The read requests are smaller. The bandwidth requirements per accelerator are smaller. And so you can get away, there's less files, and they're smaller files. But basically, you have to make sure that your storage subsystem is returning requests in a relatively narrow window to keep that one fed. And then finally, ResNet, which is, again, a vision classification training that does multiple reads per file. So unlike the first one, which is very serialized, and the second one, which does smaller requests and is latency sensitive, this one does a similar I/O pattern in terms of read requests and size, but it does a bunch of reads per file, and so again, you can take advantage of cache a little bit better in ResNet 50. Some key takeaways: the size is scaled against your client memory. I want to say 3 to 5x. I forget the exact number. But you can artificially change your client memory to make the test actually run in a humanly reasonable amount of time, and that's legitimate. They have no issue with that. They just want to make sure that they're outpacing the client memory. They do not say you cannot use NVMe local to the clients, and so that is an important thing that I'll continue to harp on, and in my closing thoughts, we'll talk about PCCRO being a huge win for this specific benchmark and for Lustre generally. The dataset generation comes right before the benchmarking. So again, there's like locality here that you can take advantage of. If you're OSS, they have sufficient memory to have this in cache. You can avoid hitting disk entirely. And achieving on all three workloads, it requires a fairly powerful system because you have to have low latency, high throughput, and have some smarts about rereading objects and not going directly necessarily to the storage to do so. So that is something that Lustre can do. It just depends on the configuration of your Lustre file system. Looking at the changes that have come in 2 versus 3, so not only are accelerators moving forward, they moved from the A100s and H100s to B200s and MI355s. The models for training have completely changed, and they've gotten rather ridiculous in terms of the bandwidth required. So you really need a very high throughput file system to keep these ones fed. The data loaders have also changed, so TensorFlow has been effectively dropped due to most people in reality switching to PyTorch exclusively. Parquet as the subsystem format has also been picked up. And yeah, the min AUs have also changed specific to those training workloads and what tends to be seen in the field. There's a number of other values on the right side here. I'm not going to go into it too much because, again, these are still getting baked, especially like making sure the data loaders are efficient and all the optimizations that are available to people in the real world doing this training are applied to the benchmark is something that's still being worked on by the developers. But very shortly, 3.0 will come out and people will be able to submit their results. Checkpointing has largely stayed the same. I think the only difference here is direct I/O is available as an option, which was not available previously, which opens up some interesting possibilities for Lustre. The rest of it is really incremental. The rules are much the same and the models are all the same. KV cache is the brand new one for inference. So this one has been asked for by a ton of people. Inference is a very important topic to many folks working in the AI space. It's essentially finally monetization of all of the effort here around training. Now that models are essentially good enough to really make some money with it. But that has shifted some of the I/O flows away from emphasizing training and towards supporting all of the users actually taking advantage of these models. So again, they're still working on this, so I won't go super deep here, but I wanted to highlight that this is now available. So if Lustre will work very well here. I think the earlier talk by DDN highlighted some of the tips and tricks you can play to accelerate these workloads. And again, this allows you to run that kind of a workload on your Lustre file system without having any GPUs or without stealing GPU resources from other people in order to get some ideas on how well your specific configuration and system will run inference. This is a quick slide if you just wanted to get up and going on MLPerf, what it looks like. You can essentially just check out, clone the repository, and then get started with generating the data set with the top leftmost one. This is again for V2, so I'm not sharing V3 instructions here because they may flux. You specify the max number of accelerators that you want to simulate, the accelerator type, give it a result stir, and then it will go and take some time generating all the files that you will then use in the real training run, which is where you generate your numbers. It spits out the command that's required to run to generate the data, similar to spec SFS, if anybody's used that. There are certain tunables in the configuration file you can play with to get better results, but there are some that are strictly verboten in terms of what you can change for a submission run. And then you run the actual the benchmark, which is in the bottom right-hand corner. Some final thoughts. Lustre AI and MLPerf. There's a bunch of ways that we can approach trying to convince everybody out there that Lustre is still very relevant for all the different ways in which AI is slamming our storage subsystems. I think the best revenge for those folks might just be posting some great numbers. And I think MLPerf's a great way, if you don't have access to the most insane GPUs out there, which is, I think, even my case most of the time, it's a great way for you to take your system on a down weekend if you have some maintenance and you get done early and you have something set up and you're like, okay, let's gonna give this a spin. You might be able to submit great numbers or even reveal some insights about how your storage could be configured differently to support the people that are likely running some of these workloads on there. Again, it's not just about the top N on this list. If you don't have a large system, if you have something that's non-Lustre that would be interesting to somebody else, please give it a spin. There are already great Lustre results on V2, I think from DDN, in fact. So I expect plenty more for V3. We're certainly looking at it. I hope the other hyperscalers take a look at it as well. And the developers should definitely take heed about this benchmark. I think that playing with this, and I think I even heard Andreas mention something about MLPerf, so I suspect this is already something people are looking at. But if we're doing it right, and I think we already are, we have all the right bits here between PCC, some of the read-ahead work, et cetera. It very closely approximates how people are really using AI in the world, and so emphasizing, prioritizing the features that we have out there that we may not have landed that can accelerate some of these workloads will not only be great marketing material for Lustre, but I think will also take some of the load off of the other users that aren't using AI that would still like to use the Lustre file system while their AI peers are otherwise consuming the entire thing right now. I think that's it. I'm a little early. Happy to take any questions.
Thank you. Thank you, Ellis. That was fantastic. Timely for me, because I've been trying to look at that stuff too. But let's open the floor for questions. Does anybody have?
So as inferencing techniques develop, you'll be adding more benchmarks. If somebody has a unique new way of doing inferencing, what does it take to, say, create your own benchmark within the suite?
Well, so there's anybody can join the MLPerf Storage call. Like you can go on the site and there's instructions on how to join the group. At that point, there are sub-working groups within MLPerf Storage, and in fact, on the KV cache one that's new to V3. There was a ton of work over the last year to basically get this up and running. If you wanted to use a different model for KV cache, like a different storage, different organization of the framework that's shown here, I'm sure you could argue for that. I think the thing they usually emphasize is, can you list like 5 places that are doing it this way? They really try to make sure that whatever they're doing, the way in which they're doing, which is why they switch from TensorFlow to PyTorch exclusively, is just because that's the way the world's doing it today. So if there's a KV cache alternative out there that you can say this is really how inferencing is done, I think they're very open-minded about adopting additional frameworks. They may ask you to submit the code for it, but besides that, they're definitely open-minded about it.
Thanks.
Hey, Ellis, Corey Spitz at NetApp. In previous renditions of MLPerf Storage, I know you could have like these insane numbers of simulated GPUs. And in fact, I think you had like 200 on one of those slides. Is there any, so one, is that going to go away? I noticed on their last slide, you said, just use 8.
I was using a wimpy system, so that was just an example of
So I'm a little worried that we're gunning for a benchmark that shows, I can run 300 GPUs on my node, and that's like going to be meaningless because nobody can build that.
Yeah. So they have a client count that you have to list, you have to list it regardless how many clients you used for the workload. For sure, there are numbers on the results that are beyond, like, I think the most that we have currently in Azure is like 8 per node, which is like an insane thing, and I don't know of too much more than that. So in reality, sure, having 300 accelerators on a single client is like not something that you can do. But the intent here is that because it's simulated, you don't care as much about the client count. They make you record the client count for like posterity, and because some people actually have NVMe on the clients, but there is no the end users that are looking at this list just to see what storage do I need effectively won't care about the client count. They're just going to look at the total number of accelerators. So if there's 320 listed, they're probably split over 320 divided by 4 or something like that. And so that it's expected that the system shouldn't care about the specific number of accelerators per client. Not all file systems work that way, but I think Lustre does, so I think that's a fair abstraction in our case.
Okay, so it's not worth worrying about then, or trying to, you had some tips and tricks for us, but there's no reason to shy away from having like 500 or whatever.
Yeah, I don't think there's any.
Okay.
I'm not concerned about the client count outside of how much NVMe I get to use PCCRO with. So.
Hi, Sergey Platonov from Zinor. Is VectorDB workload is a part of MLPerf Storage 3.0?
Is what?
VectorDB workload.
Not to my knowledge. It's listed online what all the new ones are, and I highlighted these are the new training workloads, yeah, DLRM v2, Flux, and RetinaNet, and then checkpointing's the same. They're just the Llama 3. And I'm not in the KV cache side of the house, so I can't speak to that as authoritatively, but to my knowledge, no, I don't recognize that one.
Okay, other questions? Got a couple ones. Maybe I missed this. When is version 3 due to be released?
Oh, I should know this. We're in the middle of, there's like 8 checkpoints, like 8 dates within which, like, the first one that's already passed is your intent to submit. So if you're a vendor, you wanna be part of V3, you have to say, be a member of it, and you have to say, I intend to submit. Then there's a couple rounds of edits that they make to the, like, people try it out, open bugs, the working group fixes bugs, takes feedback. We've been providing some feedback to them around some of the data loaders not being as efficient as they need to be to get real results, to not be basically CPU bound on certain file systems. And they make those fixes, and we're very close to the cutoff point where they say there's no longer any fixes allowed, such that people can go and take what's like a baked version of MLPerf and run it on their systems over and over, tuning them as they go. So we're in between we're very near to the cutoff for it being baked, and then between that, I think it's like another month before you must submit results. And there's some time period after that where they go through the results, make sure you're not cheating in any way, using the configuration files, et cetera, and then publish. So I think it's between 6 weeks and 8 weeks before you'll see new results for MLPerf v3.
Great. Are there any major AI, training or checkpointing, or I guess inference, with V3 workloads that are not covered yet? That maybe V4 will cover, or do you think 3 covers most of what people care about?
That's a great question. Everything was checkpointing in V2 and before. I think inference is the big one that everyone's talking about now. I honestly can't think of anything off the top of my head that is like novel that we'll see in V4, but the space is moving sufficiently fast, and I'm only an AI person by requirement, not because that's my field of study, so I won't speculate on what's coming next. I'm just not sure.
Great. Any other last questions? All right, let's give Ellis another round of applause. That was great. Thanks.